In 1972, a modified Soviet helicopter climbed higher than any helicopter before it, over 40,000 feet, and then it almost fell out of the sky. The engines were gasping. The rotor blades were on the edge of aerodynamic stall. The pilots were fighting a machine that physics itself seemed determined to shut down. Visual, archival footage of high-altitude helicopter test flights cut to thin atmosphere over mountains. On paper, there is nothing stopping a helicopter from climbing higher and higher. Airplanes routinely cruise at 35,000 feet. Fighter jets go much higher. Rockets punch through the atmosphere entirely. So why can't helicopters do the same? Why do they struggle above 15,000 feet? Why do most operational helicopters avoid altitudes airliners consider routine? And why, despite decades of engineering progress, does there still seem to be an invisible ceiling? The answer isn't about engine power. It's not primarily about materials. It's about something far more fundamental. It's about how helicopters generate lift and the brutal aerodynamic trade-offs built into the spinning rotor itself. Today, we're going to break this down from first principles. High-altitude helicopter capability isn't a luxury, it's a necessity. In places like the Himalayas, mountains routinely exceed 20,000 feet. In Afghanistan, combat operations often occur above 8,000 feet. Medical evacuation in high terrain depends on helicopters reaching thin air landing zones. Visual, helicopter attempting mountain rescue at extreme altitude. A fixed-wing aircraft needs a runway. A helicopter does not. That vertical lift capability makes it irreplaceable for mountain rescue, offshore oil platform operation, high-altitude military logistics, urban rooftop access. But that same vertical lift capability is exactly what limits its altitude. Let's strip this down to the most basic physics. A helicopter flies because its rotor blades accelerate air downward. By Newton's third law, if you push air down, the air pushes you up. Lift equals mass flow rate downward velocity change. Visual, simple diagram of rotor disc pushing air down, reaction force upward. Now, here's the key question. What happens when the air gets thinner? Air density decreases with altitude. At sea level, 1.225 ggm at 20,000 feet. 65 ggm, that's almost half. So if density drops by half and you want the same lift, you must push twice as much air or push the same air twice as fast. But a helicopter rotor has limits on both. Helicopters use a large spinning rotor disc to move a column of air downward. The area of that disc determines how much air mass is available. More area equals more mass flow equals easier lift generation. Visual, top-down view of rotor disc with airflow vectors. So why not just make the rotor enormous? Because rotor size increases. Structural bending, stress tip, speed, blade weight, vibrational loads. And here's the fatal constraint. As the rotor spins, the blade tips approach transonic speeds. Tip speed equals rotational speed radius. If the rotor is too large or spins too fast, the tips approach Mach 1. Team Echo 910, shock waves form. Drag spikes dramatically. Efficiency collapses. Visual, CFD simulation showing shock formation at blade tip. This is called compressibility drag, and helicopters are constantly balancing between needing higher speed for lift, avoiding transonic shock penalties at altitude. That balance gets much worse. Here's the problem that most people don't know about. When a helicopter flies forward, one side of the rotor disc moves into the airflow, the advancing blade. The other side moves away, the retreating blade. Visual, rotor disc labeled advancing and retreating sides. On the advancing side, relative airflow equals rotational speed plus forward speed. On the retreating side, relative airflow equals rotational speed forward speed at high speeds or thin air. This becomes catastrophic. The retreating blade can experience stall. Retreating blade stall means part of the rotor suddenly loses lift. The helicopter rolls violently. Control becomes unstable. At high altitude, because density is low, blades must operate at higher angles of attack. That pushes the retreating blade closer to stall. So as altitude increases, margin to stall shrinks, control authority shrinks, safety margin disappears. Many assume just install more powerful engines. But here's the truth. Modern turbine engines, like those from General Electric or Rolls-Royce, produce tremendous power. The issue is not peak power, it's air mass flow. Turbine engines themselves suffer at altitude. Jet engines require oxygen to burn fuel. Less oxygen equals less combustion energy. Visual, cross-section of turboshaft engine showing airflow path. Yes, Compressors help, but they can't create oxygen. They only compress what's available. So at altitude. Engines lose powerators, need more power, blades are closer to, stall tips are closer to, compressibility variable gets worse simultaneously. That's not a coincidence. It's physics stacking constraints. Fixed-wing aircraft have something called coffin corner where stall speed and Mach limit converge. Helicopters have a version of this too. At high altitude, lower density, higher required blade angle, stall risk, higher rotor speed. Tip compressibility risk. There is a narrowing safe envelope, visual graph of altitude vs operational flight envelope narrowing beyond a certain altitude. No amount of pilot skill can compensate. The rotor simply cannot produce stable lift. In 2002, a specially modified Eurocopter helicopter climbed above 40,000 feet. It required stripped down weight optimized blades, perfect atmospheric conditions, and it had almost zero safety margin. That was a record, not an operational capability, and that distinction matters. Part 8 Why airplanes don't have this problem. Airplanes use forward motion to generate lift. Lift equals Vs cliff density drops. Airplanes simply increase forward velocity. Helicopters cannot rely on forward speed the same way. Their lift must exist even at zero forward velocity. That's the core difference. An airplane trades runway length for altitude. A helicopter trades rotor disk area and blade speed. Different physics. Different limits. Engineers have tried. Larger rotor discs, composite, lightweight blades, advanced blade tip, chapas, coaxial rotors, compound helicopters, visual, exploded view of composite rotor blade structure, composite materials, reduce weight, advanced blade tips, delay shock formation, coaxial systems, balance torque without tail rotors, but none eliminate the fundamental. Lift requires mass flow requires density, density decreases with altitude, there is no workaround to the ideal gas law. High altitude helicopters are extremely specialized. Exponent payload to operate at extreme altitude. You must reduce weight, which reduces payload, which reduces usefulness. So from an economic standpoint, why design a helicopter that carries almost nothing at extreme altitude when a fixed-wing aircraft can do it more efficiently? Engineering is not about breaking physics, it's about optimizing within it. Helicopters can fly high, but not very high. Not because engineers lack creativity, not because engines are weak, but because the spinning rotor is an elegant solution built on a fragile aerodynamic balance. The rotor must avoid stall, avoid compressibility, unstructural integrity, compound for falling densitile at once, and nature narrows that window with altitude. Could materials improve? Yes. Could control systems get smarter? Absolutely, but unless we change the way lift is generated, unless we abandon the conventional rotor, there will always be an invisible ceiling. That ceiling isn't political. It isn't technological, it's aerodynamic, and it reminds us of something fundamental. Human ingenuity can stretch the limits of nature, but it cannot erase them. If this video changed how you see helicopters, imagine what we'll uncover next. Subscribe,